Welcome to Learning with Philemon. In this video, we will be looking at the different types of intermolecular forces. Before starting, we need to distinguish between two terms that are often mixed up. Intramolecular forces refer to the forces that hold atoms together within a molecule. Examples of these are covalent and ionic bonding. For example, in a hydrogen H2 molecule, the two hydrogen atoms are held together because both positively charged nuclei are attracted to the shared pair of electrons. For more on covalent bonding, please watch the suggested video. A covalent bond is therefore an intramolecular force. Intermolecular forces are forces of attraction or repulsion between atoms, ions, or molecules. Three types will be discussed in this video: London, dipole-dipole interactions, and hydrogen bonding. The dotted line between the two hydrogen molecules represents the intermolecular force of attraction, in this case a London force between them. Note that intramolecular forces are stronger than intermolecular forces. It takes a lot more energy to break a covalent bond than to overcome an intermolecular force. A common misconception is that when you boil a substance, such as hydrogen, you break the intramolecular bonds. In reality, you overcome the intermolecular forces. For more on state changes, please watch the video Kinetic Theory of Matter. Now let's explore intermolecular forces. London dispersion forces are the weakest intermolecular forces that molecules experience. As we learned in the video Molecular Orbitals, electrons in a hydrogen molecule occupy a bonding molecular orbital, as depicted in this diagram. The black dots represent the hydrogen nuclei, and the blue part represents the orbital. The electrons can be anywhere within this orbital. Temporarily, both electrons may be on one side of the molecule. This creates a dipole, meaning that one side of the molecule is slightly negatively charged, as seen by the larger electron cloud and the delta minus, and one side is slightly positively charged, as denoted by the delta plus. If another hydrogen molecule is next to this hydrogen molecule, its electron cloud will be affected. As like charges repel, the electrons from this hydrogen repel the electrons of this hydrogen. The electrons move to this side of the molecule, creating an uneven distribution, a dipole. These two dipoles attract each other. The positive end attracts the negative end. We can also draw this without the electron clouds, as seen in this diagram. London forces are a weak force because these dipoles are temporary. When the electrons move back to an even distribution, there are no dipoles. London forces can also be called temporary dipole forces. However, London forces do get stronger as the number of electrons in a molecule increases. When there are more electrons, a stronger dipole can be formed. The difference between the charge of one end and the other is greater if you have more electrons. The boiling point of fluorine, F2, is minus 188.1 degrees Celsius. The boiling point of chlorine, Cl2, the element just one period down, is negative 34.04 degrees Celsius. A fluorine molecule has a total of 18 electrons, whereas a chlorine molecule has a total of 34 electrons. Remember that the number of electrons can be found by checking the atomic number of each element. Both fluorine and chlorine are diatomic. Textbooks usually describe the trend in London forces in terms of molecular mass, mR. The higher the molecular mass, the stronger the London forces. Of course, as the molecular mass increases, so does the number of electrons. Now let's look at another type of intermolecular force. Dipole-dipole interactions are a stronger intermolecular force than London dispersion forces. In London dispersion forces, we saw that temporary dipoles form. In some molecules, the dipole is permanent. When one element is more electronegative than the other, it pulls the shared pair of electrons closer to its nucleus. This creates a dipole, as seen in the diagram. For more on electronegativity, watch the corresponding video in the Periodic Trends playlist. Note that all polar molecules have a permanent dipole. For more on polarity, watch the next video. An example of a polar molecule is hydrogen chloride. Chlorine is more electronegative than hydrogen, so chlorine is slightly negatively charged, whereas hydrogen is slightly positively charged. If two hydrogen chloride molecules are next to each other, there's an attraction between the dipoles. Let's compare the boiling points of fluorine and hydrogen chloride. Remember that all molecules experience London dispersion forces. As the molecular masses of the molecules are similar, they will experience London dispersion forces of similar strength. However, hydrogen chloride also experiences dipole-dipole interactions. The boiling point, negative 85.05 degrees Celsius, is much higher than that of fluorine. This means that more energy is required to overcome the dipole-dipole interactions between the HCl molecules than the London dispersion forces between the F2 molecules. Now let's look at another type of intermolecular force. The final and strongest intermolecular force is hydrogen bonding. Like in dipole-dipole interactions, the molecules that can form hydrogen bonds contain a permanent dipole. Only molecules that contain a hydrogen-oxygen, hydrogen-nitrogen, and/or hydrogen-fluorine bond can form hydrogen bonds. Oxygen, nitrogen, and fluorine are very electronegative elements, whereas hydrogen has a low electronegativity. As the difference in electronegativity between hydrogen and these three elements is large, a strong dipole is formed. Water, H2O, contains two oxygen-hydrogen bonds. The oxygen, which has a slight negative charge of one water molecule, is attracted to the hydrogen, which has a slight positive charge of another water molecule. This attraction is called a hydrogen bond. This strong interaction explains the unusually high boiling point of water. Water has a low molecular mass, like methane, CH4. Methane molecules experience weak London forces and have a low boiling point of minus 161.6 degrees Celsius. Due to the strong hydrogen bonds, water has a boiling point of 100 degrees Celsius. Hydrogen fluoride, HF, also has a low molecular mass, but due to hydrogen bonding, has a much higher boiling point than methane. In conclusion, the three intermolecular forces in order of increasing strength are London forces, dipole-dipole interactions, and hydrogen bonding. To determine the intermolecular forces that a molecule experiences, we need to consider the polarity of the bonds, but also the symmetry. This is the topic of the next video. Thank you for listening. To consolidate your learning, try to answer the questions in the description. If you haven't already, please subscribe for more content. Stay curious.